In this video, we're going to identify if a function is linear, exponential, or quadratic by simply taking a look at its table. So here we see a table, and I'm going to tell you in advance that this table models what's called a linear function or a linear equation. So this, if we think about it, we know a linear equation or a linear function forms a straight line. So the table below actually models a linear equation, and if you take a look at the table, hopefully you're noticing a very, very distinctive pattern. And if I take a look here, what I notice if I look at just the x values first is I notice that as I move from left to right, I'm always adding 1 to my x values. And then what I notice if I look at the y values is I notice that I'm always adding 3. And what I'm noticing here is that as x adds a value, y adds the same value each time. So as x increases by 1, y always increases by 3. And this consistent addition, or this repeated, and you want to probably put in there that it's consistent, this repeated or consistent addition is the pattern that we're looking for when we're looking for a linear function. So essentially, as x adds a specific amount, y also adds a consistent amount. That's the pattern that we are looking for. So if we see this pattern, we know that we're going to have a linear equation or a linear function. So then what we're going to be asked to do is we're going to be asked to write an equation for it. So this is where you have to remember what we learned about writing linear equations earlier in algebra class. So if we think back when we learned about linear equations, what you're hopefully all remembering is that the general form for a linear equation is a very special form that's consistent with all lines. And we constantly saw this. We saw y is equal to mx plus b. So this is what's called our slope-intercept form. And we wrote a lot of equations into this form. So we have slope-intercept form here. Y equals mx plus b. And what you should also know is you should know that m represents your slope and b represents your y-intercept. So what we're going to have to find here is we're going to have to write an equation, and we're going to have to find m and b in order to write our equation. So to start, I start thinking through, how do I find m and b? And the first thing I think through is I learned how to find slope earlier in this class. I know slope is y2 minus y1 over x2 minus x1. So what I can do is I can pick 2 points down below. So say that I'm going to pick this as point 1 and this as point 2. So we can do x1, y1, x2, y2. So here if I substitute these values in, I see, okay, I take y2 minus y1 over x2 minus x1, okay? So then I have 1 that turns into plus 2 over negative 1, that's also a plus 2. So this turns into 3 over 1, or 3. So by using the points down below, I found that my slope is equal to 3. Now what's also kind of cool is you can see this 3 over 1 part right here actually comes from, we're adding 3 every time. That's our change in y, that's our rise. We're going up 3, and then we're going to the right in the positive direction 1. So we can see that those repeated additions, so in this case, y added 3, x added 1, our slope is really how we change y over how we change x. So we can see that our slope is 3 in a variety of ways. Then from here, I also need to find the value for b. So I'm going to look and say, okay, well, if I want to find the value for b, I know that b is my y-intercept point, so b is going to be a point. And the one thing that I know about that particular point is that at the y-intercept value, x is 0. So what I can do then is I can look at my table and I notice that when x is 0, y is 4. So this is actually my y-intercept point hidden inside of my table. So when x is 0, y is 4. So what that's telling me is that b is equal to 4. So what I can now do is I can not only find out if my table is linear, exponential, or quadratic, but I can then write an equation for it. So now if I write an equation for this situation, I'm going to use y equals mx plus b, but I'm going to replace m and b with the values that I know that they're equivalent to for this function. So y equals my slope of 3 times x plus my y-intercept value of 4. So now not only have I determined the type by looking at the table, but I've also written an equation to model this data in y equals 3x plus 4. So now let's take a look at exponential equations. And what I notice here if I look at the table is I notice that similar to those linear graphs, I have repeated addition going on with my x values. So x is always adding 1. But then if I look down below at my y values, if I look for an addition pattern, what I notice is that here I add 2, here I add 4, here I had 8. So that's not really consistent there. But what I notice instead is that there actually seems to be a repeated multiplication going on. So here we're multiplying by 2, multiplying by 2, multiplying by 2. And I notice that every single time as I move from left to right within my table, every single consecutive y value is being multiplied by 2. So when we have this repeated multiplication pattern, we can identify that we have an exponential equation or an exponential function. So that's the pattern that we're going to see with exponentials. Now, we also had a very unique equation type here. So with linear graphs, we had y equals mx plus b. With exponential graphs, we had y is equal to a times b to the power of x. So we had a very, very specific equation here as well. And what happened is within this equation, we have two special values that are not x and y. We have our a value and we have our b value. And when we studied this particular topic earlier, we talked about a and b, and a is our starting value, which is our y-intercept value. It's where we cross the y-axis. So that's going to be when x is 0, and in this particular case, if I look at when x is 0, y is equal to 8. So what that's telling me here is that my a value is equal to 8. That's where I start on the y-axis. That is my y-intercept value. Then b, if I look up here, this exponent tells me that b will be repeatedly multiplied. That is called my multiplier. And my multiplier actually occurs down here. It's what's being repeatedly multiplied. And so in this case, b is my repeated multiplication value, which is 2. So now I can use my a value and my b value to help me write an equation to model this particular table. So I have y is equal to my y-intercept value of 8 times my multiplier of 2 to the power of x. And then finally here we have our quadratic graphs. You'll notice here again, as we look at this table down below, we're noticing that x is always adding 1, so x is a consistent addition. But here when I notice as I look at the y values, if I look for addition-wise, I notice here I essentially added a -3, added a -1, and then here I added 1 and added 3, so that's not any sort of consistent pattern. And then if I look for a multiplication pattern, I notice that there's not a multiplication pattern either. What I notice instead is that there appears to be this middle value, and then it's symmetrical on the outside of that middle value. And that's because we really have a shape that's symmetrical in a U. So when we see this symmetrical shape, and it's around a point, we have what's called a quadratic equation or a quadratic function. So that's the pattern that we're going to see. Now, we had a couple of different forms of quadratics, and so you'll be able to pick which form you actually want to write your equation into. So if you remember, previously we had standard form, which is y equals ax squared plus bx plus c. So that was our standard form of a quadratic function. We also had y is equal to ax plus h quantity squared plus k. So that was what was called our vertex form. And then we also had intercept form, which was a and then x plus p and x plus q. So you have a couple of different options here in what you'd like to do. You get to choose which type of equation you're going to write it into. So if you identify that symmetry and you know it's quadratic, you get to pick which equation type you want to write it into. Now, what I notice here is that this middle point right here, this middle point is what's called my vertex. So if I can see what that middle point that I'm symmetrical around really is, that's my vertex point. And so in this case, I'm going to choose to write this equation into vertex form. You could write it into the other forms, that's fine. I'm going to choose to write it into vertex form. So now if I start to actually write the equation for this table, I'm going to start by putting my vertex into vertex form. And what I remember is that my vertex is really the opposite of h, comma k. So this -1 I flip to its opposite, which is 1, so h is 1. And my k value is set as is, so that's -4. So what I really have here is y is equal to a, then I have x plus 1 quantity squared plus a -4. Now all I need to find here is a, and I have my entire equation. And if we think back to when we talked about quadratics, what we need to write the equation of a quadratic is we need the vertex, and then we need one additional point. So what I'm going to do is I'm going to choose one additional point from the 5 points that I have. I just need one point that's going to be plugged in there temporarily so I can find the a value that makes that point work. So here if I choose -2, -3 right here, if I substitute this in there temporarily, I can find the a value that works for that particular equation. So we have y is equal to -3 equals a, and then we have -2 plus 1 squared plus -4. Well, this inside part here becomes -1, so that's -1 squared. So we have -3 is equal to -1 squared is 1, so that's 1a plus -4, and then add 4 to each side to get the a alone, and we find that a is equal to 1. So now I can take this a value and I can plug it back into that equation, and I find that the equation that's modeled by this particular quadratic in this table is y is equal to 1 for my a value. Then I have x plus 1 quantity squared plus a -4. So to recap what we saw in these tables, when we had a linear pattern, we saw that we had repeated addition. When we had an exponential pattern, we saw that we had repeated multiplication. And then when we saw a quadratic pattern, we saw symmetry. And this all focused on those y values. In all cases, x only added 1 each time, but the y values had different patterns that allowed us to identify linear, exponential, and quadratic. So now let's practice this. So we're going to look at the table below, and we're going to identify what type of pattern this table represents. And then from there, once we know the type that it represents, we're going to write an equation for it. So here, if I look at this table, what I notice is that my x values are adding 1 each time. And then if I look for a pattern within my y values, what I notice here is that while these numbers are very small, they are multiplying by 3 every time. So I can see that multiplication of 3 each time. That repeated multiplication tells me that I have an exponential function. And then from here I need to write my equation, which is going to be written in the form y is equal to a times b to the power of x. And then here I know in this particular equation that a is my y-intercept value, which occurs when x is equal to 0. So that's where I start on the y-axis. So I can see x is equal to 0, y is 2.7, so a is 2.7 here. And then my b value is what's known as my multiplier, which we can see from the fact that it gets repeatedly multiplied due to that exponent. And my multiplier value here, I can see very clearly, is 3. So my overall equation, if I write it into exponential form, is going to be y is equal to 2.7 times 3 to the power of x. And this is the equation that models the points that are in the table I see on the slide in front of me. So if I take a look at this table on the screen in front of me, I notice that all of my x values are adding 1 each time consecutively. And if I look at my y values, what I see is I see some repeated numbers, and it looks to me like there's some symmetry. And if I start to dissect this a little bit, I notice that there's symmetry right around this point of -3, 1. And what I notice here is that it starts here and then it goes 3, 9, 19, and 3, 9. I can see the symmetry around that particular point. Due to the fact that there's symmetry, I know that I have a quadratic function. And I know with quadratics that there are 3 different forms that I can write a quadratic into. In this case, because I have this vertex point that there's symmetry around, I'm going to write it into vertex form, which is y is equal to a x plus h squared, and then plus k. And the first thing I know is that my vertex can go in for h and k as long as I flip my h value to be the opposite, so that would be 3, and my k value would stay 1 just as is. So here if I write this in there, I have y is equal to a, then I have x plus 3 quantity squared plus 1 for my k value. So now I just need to find a way to find this a value right here. If I can find a, then I have my entire equation. And all I need to find a is I need one additional point. And if I can choose one additional point from in this table here, I'll be able to actually write my equation. So if I choose one point, say I choose -1, 9. If I choose -1, 9, what I notice is that I'll find my a value that makes the point -1, 9 work. So here if we plug this in, I have 9 is equal to, my a value I don't know, -1 plus 3 quantity squared plus 1. Well, I start here, -1 plus 3 becomes 2, 2 squared is 4, so I really have 9 is equal to 4 times a plus 1. I then need to get a by itself. We divide by 4, and we find that a is equal to 2. So now I can move forward and write my entire equation to be y is equal to 2. We have x plus 3 quantity squared plus 1. All right, another example here. If I look at this table, what I notice if I focus on x's and y's separately, x is increasing by 1, and my y values are consistently going down by adding -2 to them. So I have a repeated addition here, and because I have a repeated addition for both x and y, I know that I have a linear graph. So I need to write the equation that models this table. So I have y is equal to mx plus b, and I need to find my m value and my b value. Well, my m value I know I can find by calculating slope. So I have y2 minus y1 over x2 minus x1. So if I label this as x1 and this as x2, y1 and y2, I have 3 minus 5 over 3 minus 2, which turns into -2 over 1, which is -2. And again, remember, we can also find this by taking our repeated addition of y, that's our rise, over our repeated addition of x, that's 1. we have negative 2 over 1 or negative 2. I then also need to find my b value here, which if I take a look, my b value occurs when x is equal to 0. And unfortunately here, I can't actually see what that is. I have x values of 2, 3, 4, 5, and 6. However, if I think outside the box here, I can work backwards and apply that same pattern. And I can find that when x is 0, y is 9. So I keep adding 2 since I'm going back in time, and I find that my b value is 9 if I were to keep filling out that table for when x is 0. Then I can write my equation as y is equal to negative 2x plus 9. So let's take a look at two more examples. If I look at the first table there, what I notice here is that I have x values that are constantly adding 2, so I have consistent addition among the x values, which I expected to see. And then what I notice is I have symmetry here around this middle point here. So this middle point here appears to be my vertex, and then I have some symmetry around it. So that symmetry amongst the y values tells me that I have a quadratic function. And then what I would like to do here is I would like to write the equation that models this specific table. And I'm going to utilize vertex form because I can see my vertex clearly within that table. And I know that within my vertex form, I can take the value for x of my vertex and flip it to its opposite and put it in for h, and then my y value for my vertex becomes k. So what I'm going to do here is I'm going to write that down below because I'm not quite done, but I'm closer. So I have y is equal to a, I have x minus 6 squared plus negative 4. So what I still need to find here is I still need to find my a value, and I can do that by utilizing another point. Essentially, if I take another point within this table and I substitute it temporarily in for x and y, I'll be able to find the a value that makes it true. So here I'm just going to pick a random point, so I'm going to pick the point 10, 12, and I'm going to substitute that in. So I have 12 equals a, 10 minus 6, quantity squared, plus negative 4. Well, I know 10 minus 6 is 4, and I have 4 squared, so that would become 16 times a plus that negative 4. Those are not alike terms, so I'm going to add 4 to each side. Divide by 16, and a I find is equal to 1. So what I can now do is I can write my equation as y is equal to, my a value is 1. I have x minus 6 quantity squared plus negative 4. So I have my type is quadratic, and I have the equation that models that data. Then from here I look at the next one and I notice that all of the x values are adding 1 every time. But if I look at my y values, I notice that they seem to be going down. And it seems like I'm dividing by 2 each and every time, which repeated division isn't a pattern that we talked about. But what I do know is that dividing by 2 is really like multiplying by a half every single time. So really what I have here is I have repeated multiplication of 1/2 every single time. Take 16, multiply by a half, you get 8. Take 8, multiply by a half, you get 4. So because I have that repeated multiplication, I know that I have an exponential function. Then from here, I need to find my equation. The general equation is y equals a times b to the power of x. Well, I know that my a value is my y-intercept value, which is what happens when x is 0. So when x is 0, I see y is 8. So my a value is equal to 8. And then my b value I know is my multiplier, which I can see in this case I'm multiplying by 1/2 to get my consecutive y values. So b is equal to 1/2. So now I can go and write my equation. I have y is equal to 8 times my multiplier of 1/2 to the power of x. So I know that I have the type exponential, and the equation that models this particular table is y equals 8 times 1/2 to the power of x.